Go ahead.
Okay, hello. On behalf of the organizers, I'd like to welcome you to the workshop on algorithms, quantum algorithms in number theory. We wish actually it was an in-person meeting so that we could actually meet you, but for now it's like this, and let's hope that for the next event it is in person. And as you know, usually we record, Fields Institute usually records the talks, and you can find them later on the Fields Institute channel on YouTube or its website. And if any of the speakers would not like to their talk to be recorded, please let us know in advance, otherwise we assume you're fine with it. And the other thing is that Shane Liu from the Fields Institute will help us in some things like any issues with Zoom or any other thing that you have trouble with. Please let us know if you need anything. And just let me invite Kumar Murthy, the director of the Fields Institute, for opening remarks. Kumar, really.
Okay, thanks, Armin. I'm amused because I either have to unmute myself. If I mute myself, you can't hear me. But if I unmute myself, you'll hear all the times my email goes ding, ding, ding. So if you hear some noise in the background, it's just this constant stream of emails that come through. Anyway, it's my great pleasure to welcome you on behalf of the Fields Institute to this workshop on quantum algorithms in number theory. I think it's actually the first one that we've held at the Institute, so it's a new direction. And I want to say a few words more about that later on. But for now, I'm just introducing you to the Institute. Many of you are familiar with the Institute, but for those who are new, the Institute is about 30 years old. It's a research institute located physically in Toronto. We're a network of about 20 universities, mostly in Ontario. Our activities span the entire spread of mathematics, from fundamental research to applied research, industrial research, and even commercialization. And we're interested in wherever mathematics manifests, the Fields Institute is interested in participating. The funding for the Institute comes from the federal government of Canada, the Natural Sciences and Engineering Research Council, the Canadian Institute for Health Research, and the Social Sciences and Humanities Research Council. We recently crossed this milestone where the Institute is funded by all three major research councils of Canada. We're also funded by the province, the Ministry of Colleges and Universities, and by several American foundations, the National Science Foundation and the Simons Foundation. And we're also funded by our partner universities. All in all, a very great partnership. The main thing about the Institute is we want to make it as easy as possible for people to come together and collaborate and get down to their work. So the idea is to keep the administration as light as possible. Armin alluded to the staff member who's in charge of this workshop, Shane Liu. Please do seek him out for anything that we can do to help you, so that you can stay concentrated on the science and the math that you've come together for. Notice I'm speaking as if I'm sort of an outsider, but I'm also part of this workshop. So later on, I'll come and speak from that point of view too. Now, one last thought I want to leave you with before you get started on the scientific talks is that the Fields Institute is considering quantum algorithms, quantum computation as a research theme to build. And for that purpose, we would very much like your input in terms of what are the big problems, what are the big areas or themes that we can build on. This would form part of a new initiative called Fields Magic, where we look at world-changing themes where mathematics can play a significant role. I can tell you more about the other themes when we speak a little later on. But do keep in mind as we hear each other and we discuss with each other, to try to give us some feedback on what would be a good way forward to build this as an international research theme. The pandemic has taught us to do things in a slightly different way. We're able to build research clusters and research networks which are international, virtual, and who have some sort of administrative home in a place like the Fields. institute. So that's something we're thinking about. And as I said, if there's time, I will come back to talk to you about that later on in the workshop. So for now, please enjoy the workshop, each other, and the talks, and we'll talk again later on. Armin.
Thank you, Kumar. So Alice Silverberg kindly accepted to be the chair for today, although it's very early for her. Thank you. So Alice, we are ready.
Okay, thanks. So let's see. So our first speaker presumably has slides and should share a screen. Is that right? Gabor there. And I guess we'll do questions presumably in the chat. So I'll be monitoring the chat and put your questions there, or I think you should presumably be able to just raise your hand and I can acknowledge you at the appropriate time, and you can unmute if we want to try to have a workshop, a sense of a workshop and being able to talk to each other. So if you're interested in being unmuted, raise your hand, and you can put your question in the chat in either case. Okay, so I'm happy to introduce the first speaker, Gabor Ivanyos, who'll be talking to us today on the transportation problem and related questions and some computational algebra problems for quantum computing. Okay, thank you.
Thank you for the opportunity. My main problem is obviously useful in computational number theory. However, as the subtitle suggests, my talk will be in a sort of step in the other direction. So how, say, algebra, arithmetic is useful for certain quantum algorithms. So what is the transportation problem? We have a permutation group permuting, say, points. Given 2 points, find all the group elements that transport 1 point to the other. This is either the empty set or a coset of the stabilizer, which consists of the group elements transporting the first point to itself. Often one is just happy with one element, one transporting element. Discrete log and graph isomorphisms can be cast as instances of the transportation problem in an obvious way. No, there are some easy reductions. Transportation, of course, stabilizer is a special case of transportation, but transportation can be reduced to the stabilizer problem in a bigger group. This is a least product of G by the two-element group. Even more obvious is the reduction from stabilizer to hidden subgroup. Define a function f such that to x we assign the element which carries the element carried the image of a point by x, and the level sets are the left cosets of the stabilizer. So the stabilizer is the hidden subgroup. If you are not familiar with the hidden subgroup problem, I hope this is not the case, but take this as a definition of the hidden subgroup problem. For abelian groups, this big least product can be somewhat simplified, and we get the stabilizer or hidden subgroup problem in just a group which is slightly bigger than our original group. Also, in the regular case, the transport that is when the stabilizer stabilizers are trivial, then the transportation becomes a shift problem for injective functions. Well, this is indeed mostly a toy. It is often better to consider transportation as a two-part problem. First, one has to find the stabilizer, say H, and then solve the regular case of the transportation problem in the factor group. What are the most important abelian transportation algorithms for the stabilizer problem? I hope everyone is familiar with the Shor-Kitaev polynomial time algorithm, and for the transportation problem or shift problem with the sub-exponential time algorithm by Greg Kuperberg. There are some space-efficient versions of this algorithm by Greg himself or Oded Regev. And let me mention that Regev also discovered a connection with the shortest vector problem. Probably it is less known that in special case, the transportation problem can be solved in polynomial time. This is the case when we are over an elementary abelian group where the exponent is constant. There are also some easy reductions in the other direction. We can define for each function quantum state, which is the uniform superposition of the argument and value pairs. Let us call this function graph, and when the function is on a group, then the group permutes functions and hence the function graphs by shifting the argument. And it is remarkable that given a function graph, the shift can be efficiently implemented by just multiplying the first register, the register holding the register holding the argument. And if the function was a function that hided a subgroup H, then the shifted function graphs are either pairwise orthogonal or pairwise identical states, and the stabilizer of a certain of an initial function is just the hidden subgroup H. This is actually a quantum version of the stabilizer problem in the sense that that it is not on a classical set. The permutation action is not on a classical set. Instead, it is a set of pairwise orthogonal quantum states. Well, formally, the action of G is given by oracle, and the input can be either given by an oracle or just as a stream of copies of a point whose stabilizer we want to compute, or pair of points if we are interested in the stabilizer problem. Analogously, one can define a quantum version of the hidden subgroup problem, and then these versions of the hidden subgroup problem and the stabilizer are really equivalent. So this is mainly to simplify terminology. So we can use our favorite term, say stabilizer or hidden subgroup for all of the variants, all of these problems. Let me remark that the discrete log, the famous solution of the discrete log, doesn't follow the reduction to the stabilizer outlined above. It exploits the structure of the set we are permuting, and then we go over actually an additive group, which is easier than the multiplicative group. So what are the first steps of most of the hidden subgroup algorithms? First, we prepare the uniform superposition of the group elements at the register, and using the oracle, we compute the function value in that register and then measure that register. The result will be a random level set, which is a uniform superposition of a random level set, which is actually a superposition of a random coset. Let me mention that the measurement is not necessary, but highly simplifies presentations. Well, let us look at this random coset superposition. If we do not apply the measurement, then we will actually work with a mixed state, which is the uniform mixture of the cosets of superpositions. Most, but not all, algorithms work with a stream of subgroup states as input. One can formulate a generalization of the stabilizer problem, which is related to this. So in that case, instead of copies of the input state, we may have many different states as input, but with the condition that all of them are stabilized by the same subgroup. Even this problem has polynomial query complexity by the result of Ettinger, Hoyer, and Knight. Taking superpositions of orbits is useful. Why? If we have a normal subgroup, then the factor group acts on the orbits of the normal subgroup, therefore acts on the orbit superpositions too, and that allows recursion to the factor group to compute, say, the transporting coset modulo the normal subgroup. And inside this big transporting coset, finding the small transporting coset we want is actually solving the transportation problem inside the normal subgroup. There is a connection between orbit superposition and the transportation problem, which is the following. So we would like to compute the orbit superposition, and instead we can easily compute this state on the left-hand side, this one. And this is not a good idea to highlight things. Well, on the right-hand side, it is rearranged in a way that we can compare with what we want, and we observe that the omega prime state is entangled with the transporting coset. Now it is obvious what to do. We want to clear this transporting coset, and that is, we apply the inverse of an algorithm for the transportation problem. There is an issue with this approach. To solve the transportation problem, we need several, actually in most cases many copies of the two states. There is a workaround. We can replace our original set omega by say many identical copies of states, and let act the group on these. This is an equivalent permutation action. However, we can compute with this. No, this is how to get a sub-exponential time hidden subgroup or transportation algorithm for solvable groups. The key observation is that solvable groups have a relatively short normal series with abelian factors, and recursion along this short series using the available abelian transportation algorithms, we obtain a sub-exponential time algorithm for the whole group. Well, in special group that are constant step solvable and of constant exponent, then we can use the polynomial time shift and hidden subgroup algorithm, and this way we get a polynomial time stabilizer and polynomial time transportation solution in G. Well, this is an example for a quantum algorithm that doesn't work with subgroup states. Now I am turning to show you how this less known polynomial time abelian shift algorithm works. In general, already mentioned that the interesting case is when the abelian group already regularly acts on the set, and we want to find the transporting element, which is a singleton. We define a function on the direct product of A with the set of two elements. Actually, this can be imagined as a semi-direct product, but it is not necessary to see that. Here are the level set superpositions. And now, if we apply the Fourier transform of A and measure the character, again, the measurement is not necessary, we obtain a qubit. Now, specializing to elementary abelian groups, we do the following. We measure the qubit in the Hadamard basis, and if we happen to get the second basis element, then we can be sure that the character value on the shifting or transporting element is not 1. Using the duality between characters and group elements, this way we will get a uniformly random sample of vectors U from those which are not orthogonal to the sought element. And we proceed with a, say, sort of standard method. We consider this polynomial. This is a polynomial in U. The coefficients depend on S, and we get a lot of zeros, and that many random elements will determine the coefficients of the polynomial, and therefore the shifting vector S. If you expand this, then you see that either P or N is in the exponent. One or method is better if the P is smaller. So especially for constant P, it is polynomial. Now I state here a nice problem. Let us call it hyperplane cover. The decision version of finding the shifting vector is reducible in the regime when P is of small or medium size to a sort of decision version, and no, the problem is that that given hyperplanes in the space, do they cover the whole space? This is, of course, complete already for P equals 3. But we are interested in a sort of average case relaxation of the problem. How many random hyperplanes we need so that the fact that they cover the space can be proved in time polynomial. So a weakness can be found in polynomial time. The algorithm presented before is suggests that for constant P polynomial size sample is a polynomial number of random hyperplanes are sufficient. But well, actually, a number of hyperplanes that is polynomial in both n and p is sufficient to cover with good probability. So the open question is whether there are some worse, whether there is a little bit or much worse bound such that many random hyperplanes are sufficient to provably cover the space. I skip this slide. Maybe I will have time to return to this. And let me turn to the other main topic. This is the stabilizer or hidden subgroup problem in nilpotent groups. A group is nilpotent if iterated commutators become trivial, and the smallest C, such that C for commutators become trivial, is called the nilpotency class of the group. For constant nilpotency class, the really interesting case, the key case, is when our group is a P group of exponent P, and the hidden subgroup problem is hidden subgroup is as small as possible. Here is an example of a class 2 group. These are the 3 by 3 unitriangular matrices over the P element field. No, in class 2, we can manipulate representations in a nice way. The whole idea comes from representation theory, but also has an elementary version. I will present here the elementary version. But to representations, the group has certain nice automorphism called sigma k. Sigma k raises to the k power modulo the commutator, but raises to the k squares power inside the commutator. And the latter allows us to nicely manipulate representations by the formal property ensure that our hidden subgroup problem do not move too much. It remains the same modulo the commutator subgroup. Now the elementary approach. We have a superposition of a coset, and we would like from that create the superposition modulo the commutator subgroup. And then we take several copies and compute the hidden subgroup modulo the commutator group with the abelian hidden subgroup problem in the factor by the commutator. And then we will find the hidden subgroup in this smaller group, which is in our case commutative. No. So what to do? So we want to create this coset superposition modulo the commutator. We add the uniform superposition over the commutator and apply multiplication, and we get this superposition. And now or exponent p is too large, so we cannot clear this undesired element using the inverse transportation problem. Instead, we use the Fourier transform of the commutator and hope that the character becomes trivial. Of course, the commutator group is too large, so it is very unlikely. But still, we can take several copies and somehow let the characters cancel out each other. The key observation is that that one such state here is an eigenstate for the action of the commutator subgroup. Of course, the eigenvalue corresponds to the character. Now we take several copies and choose appropriate parameters k, and define an action of g on these copies. The action will be multiplication not by x, but the sigma ki of x on the i's position. What we will have that for the commutator, this composite state is still an eigenstate, and the eigenvalue will be related to the product of the k squared powers of the character. So what we want that this product of the characters become trivial, then the commutator elements will stabilize our state. So of course, this condition, if we go to the duality, will become a system of homogeneous linear equations in the ki squared values. So we have say n diagonal quadratic equations, and somehow it turns out that we need further n linear equations so that the whole so that the hidden subgroup H, the elements of the H, stabilize this state. And it turns out that in that case, the hidden subgroup is this big subgroup. This is essentially a hidden subgroup problem in the factor by the commutator. Now, how many copies we need? It turns out that if n is roughly n cubed, then taking n copies will be good. We can solve the whole system if the number of variables is that big. So compared to the Chevalier-Warning theorem, which guarantees existence from n bigger than 3 times n, here the 3 came to the exponent. One could expect that solving higher degree equations help finding hidden subgroups in nilpotent group of higher class, in nilpotent groups of higher class. Currently, we know this only for a special case, namely if our group is at the same time nilpotent and two-step solvable. Then the interesting case is when our group is a semi-direct product of an elementary abelian group, say V, and with the p-element group. The action defining the p-element group is actually the unipotent matrix on the vector space, which can be decomposed as the sum of the identity and the nilpotent matrix, and the nilpotency class of the matrix coincide with the nilpotency class of the group. The hidden subgroup is actually V times Y, where Y is a fixed element from the complement, and V is an unknown element from the abelian part. If we look at the powers, we see that actually the trace of the subgroup H is a curve in the vector space parameterized by T of degree T, degree D. Now, what we do, we take the coset superposition, we apply the Fourier transform of the elementary abelian group, and measure the character, not necessary again, obtain something, so a degree D polynomial in the phase. Now we repeat this m times, so we take m such states and add again the superposition of the complement in a new register, and choose appropriate deltas such that this equation, degree D diagonal equation, holds. Subtract appropriate multiples of the last parameter from the Ti, and now obtain a new expression in the phase. And if we choose the deltas according to these equations, then it turns out that the degree D parts of the polynomials cancel out each other. So the degree will be D minus 1 in T, and degree D will be the the TIs, but we measure the TIs. Now we have degree d-1 phases and collect many copies and let the degree b-1 parts cancel out each other, and so on, until we get eventually a linear phase, which can be computed by taking the Fourier transform. It turns out that this gives a linear constraint for the coefficients, a sort of random linear constraint of the coefficients of the polynomial, and we collect many such equations and eventually determine the polynomial. And from the polynomial, we finally determine the hidden vector. So what we need to solve this diagonal system of equations by the Chevalier-Warning theorem. There exists a non-trivial solution if m is bigger than d times n. We would need a polynomial time effective version. So we take bigger m and hope that we can find a solution in times polynomial in the whole input. And we have a solution for that. Unfortunately, the pattern observed in earlier continues, that d is in the exponent. So the open question is whether there is a bound closer to polynomial, and maybe the case d equals p-1 deserves a special attention. Then the problem is just finding a non-empty subset of the input vectors such that the sum of the subset is 0. One could call an appropriate n an effective Davenport constant for the vector space. And let me conclude with a slide summarizing the two main problems I considered here. One is the hyperplane cover, and the second one would be the effective Chevalier-Warning type problem, solving the system of diagonal equations. For special Ds, one can have some slight improvement, but still, so the exponent, if d is a power of 2, then simply d appears in the exponent, but it is only a slight improvement. Question is that somehow all available algorithms are completely deterministic and worst case. well, the question is whether the average case situation, we actually have an average case problem, can be used. So is there something much better in the average case? We do not know. Also, somehow, or algorithm for D equals P minus 1, so this is the zero-sum subset problem. Everything we know is also a solution for a general D. But for this problem, ozone has a nice proof of the existence of a zero-sum subset. So one can hope that there is a different algorithm which works. And I think I thank you for your attention with this slide.
Hey, thank you very much. We'll applaud either by unmuting or Zoom. So thanks very much for the talk. Are there any questions? You can either unmute and ask your question or ask in the chat and I can read the question. Gabor, I guess you had a slide that you said you'd go back to if you have time. I think you do have time if you're interested.
Yes, then
Slide 16.
let us go back here and just one slide back. No. I have to go here and
Previous.
no, somehow
Right?
it is not that easy to find.
I think it's this one.
Yes.
Next one.
Here, this is the multiple shift. So in that case, so this is a generalization of a shift. We have in the original case we have a sequence of two elements. No, we have a longer sequence. It is somehow there is a typo here. So I would mean U plus T times S, where T is from a subset of the group. And for the one-dimensional case, there is a polynomial time algorithm by Childs and Van Dam, which works in the case when k, the length of the sequence, is inverse polynomial in P. And in that case, the sequence must be contiguous. And recently, solutions found in the multidimensional case when the set is almost all the group elements except a constant number of elements. It doesn't matter which are missing. This is actually a direct generalization of for abelian shift algorithm. Well, at present, we do not have anything better. Maybe a modest open question would be if, say, we have if we have a fraction of elements, and we can allow that that the sequence, or we can require that the sequence is contiguous. Well, if P is much larger than n, then it is obvious. So the question is for the case when n is large and large compared to the length of the sequence, or large compared to P. Sorry, large compared to P. So this is a further question. It is related to really the hyperplane cover problem.
Maybe to open it up to wider discussion, I'll suggest that the recording